Here is a section that's crucial to what we're going to be doing for the rest of the semester. It involves something called linear independence. And let me write up an example here to show you sort of an idea of what this stuff means. So we'll start with a homogeneous system of equations. And you may remember that that is a system where the answer column is all zeros. So as usual, I'll set up not quite an augmented matrix, and since the other side is all zeros, I'll just work with the matrix itself. So I'll multiply the second row by 5 in an effort to wipe it out in the next step. And now I'll go ahead and take out that as much of the second row that I can. So I'll take out the 20. And let's see, negative 4 times negative 3 is 12 plus 35 is 47. And once again, I know the other side, the zeros that I didn't include. That's nice. I can divide the second row by 47. And then I can take out that negative 3 as my next step. And I can finish it off and get a nice perfect looking result if I divide the first row by 5. You remember, since the other side is 0, what I have is x equals 0 and y equals 0. This is the only solution. So here's what we were solving. Here's the original system of equations. I had x times 5, 4. You remember I had a 5x and a 4x. And y we had negative 3 and 7. And of course that system of equations equaled zeros. So the only solution is where x is equal to 0 and y is equal to 0. So you can see we don't get an infinite number of solutions like normal. I have one and only one solution. That's crucial. So this is important. We call the vectors (5, 4) and negative 3, 7 linearly independent. That means that there are no other numbers besides 0 and 0 that will work for x and y. That's the notion of linear independence. Let me go ahead and write the formal definition down, and it goes like this. A set of vectors, let's call them V1 up to VP, is called linearly independent if the only solution to x1 v1 plus x2 v2 plus dot 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 plus xp vp equals the 0 vector, the only solution to that is x1 equals x2 equals dot 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 equals x sub p equals 0. So the only solution is equal to 0 in the scalars. That's what linear independence means. And so the point of this section is to try to get you a feel for this and to maybe do a couple proofs so you get to understand the true ramifications of it. Let me go ahead and underline linearly independent. So we know that was the key phrase there. And let's do some examples. So let's determine if the set, what do we have here? 1, 4, and 2, 8 is linearly independent. You try to use exactly the same notation I used in the definition. So what that means is I'm trying to solve the following for x1 and x2. So I want to figure out what are all the values for x1 and x2. If I find out that x1 and x2 both have to equal 0, then I know they're linearly independent. If either one of those or both of those is not 0, then they're not linearly independent. So immediately I'll go to a matrix. Remember, once again, I don't have to augment the matrix because I know the other side is all zeros. So let me target that 4 in the bottom left corner. And you'll see I wipe out the second row completely. What this means is that x1 plus 2x2 equals 0. Or another way to put it is x1 equals negative 2x2. So now I know, since I have an infinite number of solutions, this is not linearly independent. So for example, if x2 equals 1, then x1 would equal negative 2. Let's put those numbers in the spots. So I'll put negative 2 in for x1, and I will put the number 1 in for x2, and let's see what we end up getting. When I multiply the negative 2 through, I'll get negative 2, negative 8. Well, you can see what's going to happen here. So we have a non-zero solution. Since at least one of x1 or x2 can be non-zero, or both, we have that the vectors are linearly dependent. Basically, that's all there is to it. If they're not linearly independent, they're dependent. So you don't have a choice in the matter. I mean, there's no third choice. There's just those two. So we now note that I don't have to have both of x1 and x2 be different from 0. I only need one of them to be different from 0 to prove linear dependence. Let's move on. Let's determine if the columns of the matrix are linearly independent. So taking my cue from the last time, let me go ahead and, well, let me put the matrix down first. We have -4, 0, 1, 5. Looks like I didn't make my matrix lines big enough. Then we have -3, -1, 0, 4, and then 0, 4, 3, 6. Okay, so we set up an equation. And once again, I'll set up an augmented matrix. The only reason I did this was to show you that I'm still doing this more than I think I need to do so that you get comfortable going from a matrix to the vectors and back and forth and such. So when I go to do the augmented matrix, remember I don't need the answer column because it's all zeros. First thing you're going to want to do probably is take this 1 that's right here and move it up to that spot. It's the best thing to be up there. So I'm going to go ahead and put it there and swap rows 1 and 3. So row 1 will be swapped with row 3. And so row 3 is 1, 0, 3. It goes up there. And then we have -4, -3, 0 there. Now one thing I know, I like this, there's a 0 in this spot right here. That's nice because it's already got the thing started. I won't have to go and clear that out. I will take out this -4 and this 5 though. So I'll do 4R1 plus R3. I'm not going to touch R2, so I'll just copy it. And then when I do 4R1 plus R3, I take out the -4 like I wanted. This -3 is untouched because of the 0 in that spot. And then 3 times 4 is 12, plus 0 is 12. And then we have, taking out this, I'll do -5R1 plus R4. And once again, this 4 down in the bottom is unchanged. 5 times 3 is 15 plus 6 is 21. Now let me use this -1 here to wipe out the things below it. Now, for these kind of questions, I don't have to go all the way. I just have to get to the point where I know if it's going to be a unique solution or not be a unique solution. A unique solution meaning that the answer is all zeros. So I will do -3R2 plus R3. So it looks like -3 times -1 is +3. As I wanted to, I take that thing out. I already had a 0 here. And then, well, -12 plus 12 will be 0, so I've zeroed out a row. You might as well give it up. Well, I don't know about that. That's not necessarily true just yet. I have 3 variables, x1, x2, and x3, and I have 3 columns, but I have more than enough rows. It's possible this thing is going to have a unique solution still yet. Let me wipe out this 4 that occurs down here. I'm going to multiply, let's see, 4R2 plus R4, and then I have 16 plus 21 is 37. All right, I've caught a mistake. Let me fix it before I go on here. When I did negative 5r1 plus r4 right here, this 3 times negative 5 is negative 15, plus 6 is actually negative 9. Let me fix that. Now the next step is still okay, except this number is probably not going to be okay. So when I did 4r1 plus r4, I get that. 16 minus 9 gives me a 7, not a 37. All right, so I think we're okay there. Now, once again, I can divide by the 7. You know what, and I'll stop here, because right now I know that x3 is equal to 0. Now, come up here. This says negative x2 plus 4x3 is equal to 0. But if we know x3 is equal to 0, I also know that x2 is equal to 0. So x2 and x3 are both 0. And then finally up here I have x1 plus 3x3 is 0. And, well, x3 being equal to 0 means that x1 is equal to 0. So right now I get there is only one solution. x1, x2, and x3 are all 0. So since that's the only solution, so since 0, 0, 0 is the only solution, the columns are linearly independent. Let's do another example, same type of an example. I want to determine if the columns are linearly independent. So it's the same deal. I'm going to have myself a matrix, and I have 1, negative 3, 0 for the first column, negative 3, 7, 1, 3, negative 1, negative 4, and negative 2, 2, 3. And once again, I'm not going to bother in breaking it out into vectors and everything like that. I know that if I make this into an augmented matrix, I will have a column of zeros off to the side, and I don't need to bother with that, because when you do raw operations to 0, it doesn't do anything. So let me go ahead and work this as much as I need to. I'm going to first target that negative 3 in the first column. So I'm going to do 3r1 plus r2. So let's see what happens here. Negative 3 times negative 3 is negative 9, plus 7 is negative 2. And then we have 3 times 3 is 9, minus 1 is an 8. And then 3 times negative 2, negative 6 plus 2 is negative 4. And then I don't need to do anything to this one. It's already done. Now, let's pause here for just a moment. If you look, it's beginning to shake out now. If you look here, in fact, I probably didn't even need to start the whole thing. I am going to have a pivot right here. And I can see, using this negative 2 to clear things out, I am going to have a pivot into that spot right there. Assuming I clear it out, so I take negative 2, half it to take out this 1, then I'll probably take out this thing also. But when I do half of the 4, I'm not going to any way, shape, or form get a 3. So what's going to happen is it looks to me like the next pivot is going to be all the way over here. Probably when I do my next operation, if I divide, just follow me for a second. If I divide this row by negative 2, I'll get 1, negative 4, and then I'll get a 2. And then if I take the negative of that and add it to that row, the first 2 entries will disappear, and I'll be left with a non-zero entry here. So there's my 3 pivot columns. Unfortunately, to have a unique solution, you need a pivot in all of the columns. I don't remember where it was that we did this before, but we need, let me write this, in order to have a unique solution, we need a pivot in every column. Let me just follow this here a little bit. Suppose I were to continue this. Right away you would see, if I were to continue and have zeros in these spots here, but this 3 is, or whatever is left, is a non-zero entry, I'll know that x4 is equal to 0. The problem with it is that I can use that to clear out these entries above it, and indeed I can use this to clear out the entries above it as well. However, I'm not going to be able to use this 8 to take out the 3. What I'm getting at is this. We are going to end up here with a free variable. And it looks to me like x3 is going to be a free variable. Since it's a free variable, we have an infinite number of solutions. So take a look. Here's x1, here's x2, here's x3, here's x4. And so there will be numbers left over. But even if there weren't numbers, if this completely zeroed out, even if it did completely zero out, x3 is still a free variable. And with that, we know we have more than one solution. So therefore, the columns are linearly dependent. It didn't ask me to find out any numbers that actually worked. All it did was ask me independence versus dependence. And so I only need to go as far as I need to go until I see when I'm certain that I'm going to have more than one solution to know that what the answer is going to be. It didn't ask me for more detail than that. Here's a note. A single non-zero vector is linearly independent, as long as it's non-zero. So, I mean, if you were to take it, if v is not 0, let's just call it, not even v1, let's just call it v. So if I know that that's not equal to 0, then if you try to solve such an equation like this for x, and that's not the 0 vector, the only way to get this to equal 0 is if x is equal to 0, because if x is not equal to 0, we get the following. I could divide by it. So I could take v and get 1 over x times the 0 vector. Well, that's the 0 vector, which means that v would have had to have been 0. So any single non-zero vector is automatically linearly independent. Now for two vectors, let's call them v1 and v2 to be, it's easier in this case to be linearly dependent. I'm giving a little bit different thing here. Requires a solution to this equation that is not 0 in all of the variables. So, for two vectors to be linearly dependent requires this kind of equation be true, where x1 does not equal 0, or x2 does not equal 0, or both. Well, so what we need here is, if we want them to be linearly dependent, it requires one of the two x's to be non-zero. So we can also write x1 v1 equals negative x2 v2. And then if one of the vectors is not 0, so suppose that x1 were not the one that was 0, then I could divide by x1, like so. Then what I have is I will have one, well, it doesn't really matter. What I'm getting at is this. This implies that v1 is a multiple of v2. So basically that's what we're getting at here. So two vectors are linearly dependent if one is a multiple of the other. Of course, what would a section be without a theorem? Seems like we get one in every section. Of course, this linear independence is huge. You'll see it if you were to go in the back of any textbook of linear algebra and look up linear independence. You would see a vast number of pages devoted to just that topic. Let's suppose v1 up to vp is linearly dependent. Then at least one of the vectors is a linear combination of the other vectors. Once again, I'm going to do the proof in as simple a possible way as I can, hoping that you will follow it. So the assumption we're making is that the vectors are linearly dependent. So since v1 up to vp is linearly dependent, there are scalars x1 up to xp. This is an interesting phrase, pay attention to it. Not all 0, such that, so that's a way of saying that at least one of them is not 0. You can just say not all 0. We'd have x1 v1 plus dot 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 plus xp vp equals the 0 vector. Now we know at least one of these things is not 0. Let x sub j not equal to 0. So I don't know which one of them. I'm just saying pick one that's not 0. I know there is one. So what we can do is the following then. I'm going to rewrite my equation this way. I'm going to have x1 v1, and what I want to do is bring that thing out, or bring the focus on that particular vector. So I have xj minus 1 vj minus 1 plus xj vj plus xp j plus 1 vj plus 1 plus dot 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 plus xp vp, and all of that is equal to the 0 vector. What I'm going to do is take that x sub j vj to the other side, and here's what I'm going to get. So I'll pull out my xj vj to the other side, and what do I have left on the right? I'll have x1 v1 dot dot dot. Then I'll get to x sub j minus 1 vj minus 1 plus xj plus 1 vj plus 1 plus dot 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 plus x sub p v sub p. So you can see I've plucked the x sub j out. Now, since I know that xj is not equal to 0, I'm going to divide by negative x sub j, just like I did in that example. So vj will be negative x1 over xj v1 minus, these will all have minuses since you're dividing by the negative xj. And it seems like I have done this argument once before, so hopefully it won't seem that bad. And, well, you can see then, this implies that v sub j, oh, it looks like I forgot my little arrow above it, is in the span of v1 up to vj minus 1, vj plus 1, up to v sub p. So I have proven that one of the vectors is a linear combination of the other vectors, and that's all we needed to do. Example, let's find the values, or just value, of h for which those vectors are linearly dependent. And once again, you can set up a linear combination, set it equal to the 0 vector, or just go right to a single solitary matrix, work it until you're certain that you know what's going on. All right, I think normally I would do a swap on rows 1 and 3, but check this out. I can already see that I can wipe out the third row. I'm going to do it real quick. I'm going to do negative 1/2 row 1 plus row 3. I know I don't normally do that, but I can't resist since it's so evident to me that it will wipe it out. So when I do that, I'll get, let's see what happens, negative 1, that wipes that out. Then this will be a 3, wipes that out. This will be a negative 4, so it'll wipe that out. All right, right now we can stop because we see that we have a free variable. The best I'm going to be able to do, even if I clean up this negative 4 and even take out that 7, which is probably, well, I can see it's not going to happen, I'm going to get an infinite number of solutions. So what value of h, it doesn't matter because I already know these things are linearly dependent before I even bother with h. So no matter what the value of h, we get linear dependence. In R2 and R3, we can look at geometry and take a look and see what these things mean. So let's take a look at some geometry. So what does it mean for V1, V2 are linearly dependent if one is a multiple of the other. So in a situation like that, you'll have one vector. Let's say that this is u, and then a second vector, v, will be a multiple of it. The way I wrote this probably is not the best thing in the world. I should have written this as one of them is v1 and the other one is v2. So in that situation, one is a multiple of the other, so it means one's longer than the other, or it could also be longer but point in the opposite direction. Since we could be a multiple of the other one, negative multiples are acceptable. They just point the vector in the other direction. Now, if you have something like if, let's say, v1, v2, and v3, let's call these in R3, are linearly dependent, then what you're going to have is something like this. Probably, I mean, there's other situations than this, but what you're going to have then is you'll probably have a v1 there, maybe v2 here, and then maybe v3 here. So what is it? They're all in the same plane. You could have all of them be be multiples of the same vector. That's possible too. This is just one kind of a situation. If you want to see an independent version, here, let me come back here for a second. This is dependent. But if I wanted independent, they would have to do something like this. As we've seen before, those two vectors, if they're linearly independent, which I didn't mention in the past, but if they're not multiples of each other, they'll actually generate all of the plane. For a situation here, this is the dependent part. For independence, you could have, there are so many different things that can happen, but maybe one of the situations is like this. You could have V1 and V2 share a plane, like so. But then V3 comes in like this. I'll see if I can put it here. Remember, to give something a three-dimensional look, you have to do something like this. So that'll be V3. And you can see that V3 is not in the same plane generated by V1 and V2. So this would be an example where they'd be independent. Another theorem. Let V1 up to Vp be a subset of Rn if P is greater than N, the set is linearly dependent. This is an important one. It'll be used a lot. So what we're going to do here is I'm going to let A equal we'll use those as column vectors in the definition for this matrix here. So A is an N by P matrix. N rows, P columns. Since P is greater than N, we have more columns than we have rows. So since P is greater than N, we have more columns than rows. Well, I want you to think about this. Let's take a look here. The system AX equals 0 will have N rows and P columns. And I'll say it again, P is greater than N. Now, I want you to think about that. Is it possible then to have a pivot in every column? No, we cannot. The reason why is because we get only one pivot per row, but there's only N rows. So we have columns with no pivots. And that means we have free variables. So let me say that again. I just want to make sure that we have it. We cannot possibly have a pivot in every column. In fact, the most number of pivots we could have are going to be N of them, since you only get one per row, and we only have N rows. So now that we know that we have at least one free variable, this automatically means that there are non-trivial solutions to AX equals 0. They'd be linearly independent if the only solution was the trivial one. Here we know that there are non-trivial ones. So we now know that the vectors are linearly dependent. So that completes the proof. One thing you may, just as an example, maybe a picture of this that's going on here. Maybe let's do something like 3 by 4, something like that. And let's just think here. If I were to do, say, a 3 by 4, what I could possibly have as far as pivots goes something like this. And then I might have this, and it doesn't really matter what's up here, but you have zeros. So this is a 3 by 4 system. And you can see in this case right here, we would have free variables because I have no pivot in this column. Maybe another situation that occurs is something like this. The blocks, remember, I'm using as non-zero entries. And then we would have something like this here. This would be 0, but we'd have stars up here. I don't know what they are exactly. But you can see, once again, we're going to have free variables. In this case here, it looks like x3 would be my free variable. So you can see, I need to have the same number of columns as rows in order to have what would be any chance of linear independence. And any chance of a unique solution is only going to happen, guaranteed to happen, I guess, as much as you can guarantee it, is when the number of rows and columns match. And even then, you don't have a guaranteed unique solution, but you're going to need it for the times you have a unique solution most of the time. So basically what this says is, it's very simple. If you have more vectors than entries in each vector, you have dependence. Let me do an example. Are the vectors linearly independent? And what I have are, these are going to be in R2. I'm going to start with 1, 4, 4. And then I'm going to do -1, 3. And then I'm going to do 2, 5. So perfect application of the theorem. We have only 2 entries in each vector. But 3 vectors. So if you want to use the notation of the theorem, in the theorem we would have, for Rn, we have n equals 2 and p equals 3. And since we have that situation going on in the theorem, so we know we have linear dependence because of that theorem. As an example, let's let A equal A1, A2, and A3. And each vector is in R4. So what are the possible echelon looks is what I'm looking at. So what are the possible echelon forms of A? So this situation now has, we have more entries in the vector, so we know that we're going to have linear dependence. Let's take a look at what could happen then. We could have something like this, zeros underneath. Then we could immediately, this is as close as we're going to get, I think, to it. Let me put a 0 here. So in a situation here, let's see, we have 4, no, this is a reversal of the theorem here. Here we have more entries than the number of vectors. So since we have more entries than the number of vectors, this is a possible echelon form right here. And in fact, I believe it's the only possible echelon form, because I don't want to put the echelon down here and then have this row be zeros. So with that in mind, you can see I'm going to get a unique solution here. Even though we do have a row of zeros, it's because we had one more row than we needed. In the terms of systems of equations, you have 3 variables but 4 equations. To solve a system like that uniquely, the most you really need are 3 equations, as long as they're independent from each other. So now, sometimes if you have a 4th one, it might be a linear combination of the other ones, and that's exactly what happened here. And in fact, you're kind of forced if you reverse the theorem in your mind, I want you to think for a moment. Think across. These are also row vectors. We'll talk about that later. But if you look at these row vectors, they only have 3 entries, but yet they have 4 rows. That means the 4 row vectors will definitely be linearly dependent upon each other, which means one of them we can zero out through the row operations. And so, but a situation like this will provide us with the only echelon situation that I can think of, and it provides a unique solution. A lot of things in this course that you'll find are things like they'll want you to construct counter examples or something like that. So let me show you what I'm talking about. Let's construct 3x2 matrices. Let's call them A and B, such that AX equals 0, that's the 0 vector, has only the trivial solution, but BX equals 0 has a non-trivial solution. So what this is meant to convey to you is sometimes I have a unique solution. When I have more rows than columns, sometimes I'll be able to get a unique solution and sometimes I won't. That means I don't have a guarantee like I did in a theorem. The theorem says that if you have more vectors than rows, automatic dependency. Here we have a system where we have more rows than columns, sometimes dependency, sometimes not. There is no one theorem that works for us. So let's take a look at what A could look like. In order to guarantee us unique solutions, remember this is 3x2, we could do something like this. And as I mentioned here, then x1 and x2 are, let's see, x1 and x2 are both equal to 0, gives us a unique solution there. We only have 2 variables in this situation. But now consider the B. Let's say 1, 2, 3. Then I'm going to do 3, 6, 9. Now for B, I can use the row operations to wipe out all of the entries underneath. I'll let you do them, but what you can end up with is this. That one will have an infinite number of solutions and not a unique solution. So here is unique or trivial solution. Let's just call it trivial. And then here will be a non-trivial solution. Here I'm going to let A equal the following matrix. We have 4, -7, 9, 1, 5, -3, 6, 3, 3. And note, this is so to make it a little bit easier on you, we happen to know that this relationship exists among the columns in that matrix. So A1 plus 2A2 is equal to A3. A1, of course, is that column. A2, of course, is that column. A3 is that column. So I want to invent a vector x such that AX equals 0. And I probably should be a little more specific. You can always use x equal to 0. So I want to make sure that x is not equal to 0 when I do that. So take a look at this relationship here that we have. We have A1 plus 2A2 minus A3 equals the 0 vector. And let me put a 1 in front of that because I would like to illustrate that even more. And this is a given piece of information. You can verify it if you want. 4 plus 2 does equal, equal 6. And so 4 plus 2 minus 6 will equal 0. You can see that it will all zero out. So what I'm going to use for my vector then is this. I'm going to use 1, 2, negative 1. Watch what happens. I will leave it to you. You can do the multiplication yourself, but you will get 0, 0, 0. So notice the relationship. 1, 2, negative 1, 1, 2, negative 1. Zeros it out. We end the section with a final theorem. Any collection of vectors in Rn that contains the zero vector is linearly dependent. So for proof of this, let's take a look at what I have. My collection then I'll use as, it'll have the zero vector, but then let's say I have v1, v2, up to v sub p. And I can show you I get a non-zero solution to the ax equals 0 equation in the following format. I can take the number 1 times the zero vector, but then I can take 0 times every single rest of the vectors. And that automatically is a zero vector, because this is 0, and of course these zeros that I'm multiplying out here will zero out everything. Notice that it implies linear dependence because one and only one of these coefficients is not equal to 0. That's all I said you had to have, was at least one not equal to 0, and we have exactly one that's not equal to 0. So this implies that those vectors are linearly dependent. You've got to keep track of things, or you have to keep track of what these theorems are stating. A lot of times, especially I noticed that when I was looking at true and false questions, I was getting caught a couple of times because I didn't happen to think off the top of my head that one of the vectors would be equal to 0. Always keep that in your mind. A zero vector works as a good counterexample a lot of times.